A budget of paradoxes. A discussion of a number of features of special relativity that people have been known to find paradoxical. In common language terms, these are usually resolved by the admission that simultaneity is relative and there is no absolute time in relativity. Very long trains. The details of the meaning of the phrase relativity of velocity are perhaps better served if we consider two very, very long trains. The use of a spacecraft moving over the ground can give people the idea that one is moving and the other is not. The use of two spacecraft in space removes the intuition of distances. Both of these are retained by a pair of trains. Imagine two line worlds, Discworld only more so, like Ringworld, but in a straight line, an infinite straight line. They travel at a high speed with respect to each other, a bit like Heinlein's roads in the short story The Roads Must Roll. In this scenario, there is nothing else in the universe to suggest which is objectively moving, so each can validly say that they are nominally stationary. But only nominally. Keep in mind that in relativity, it is not so much that any inertial frame has the right to call itself stationary as that no inertial frame has that right. There is no sense in which the word stationary has any meaning other than with respect to a frame. What can be said is that the result of corresponding measurements taken entirely within each world will be the same. There is no way to distinguish the two worlds in terms of the laws of physics that they locally measure. These worlds are infinitely long and perpetually moving with respect to each other alongside each other. There is a low warning barricade at the interstice, but you can jump over it. What if you try to jump from one to the other, and back again? A basic rule of relativity is that things nearby do not change with a change in velocity. So if the clock next to you on the other line world is registering 1 p.m. before you jump, then it will register 1 p.m. after you jump. Since you are now in and stationary with respect to the other line world, your sense of time, at least in special relativistic terms, is now aligned with the sense of time of that line world. The result is a bit freaky. Before the jump, you felt that all the points in your original line world were at the same time. Now as you look in the direction you are travelling with respect to your original world, you will see the future, and behind you, you will see the past. At least after the signals have arrived and been collated. And that means that the points in your world in the direction of travel are now in the future, which maybe we can handle, but the points behind you are in the past, which perhaps we cannot handle, as it means that time went backward. If instead of a sudden change, one were to undergo a rapid but not infinite and instantaneous acceleration, then the points ahead of you would rapidly go forward in time, and the points behind would rewind to the past, going backwards. This may seem freaky, but is a logical implication of the way in which we define the past and the future for points in space that are far away from us. The amount that the events behind you rewind is only so much that it remains within the region that you have not yet got the information for. So you cannot influence the past via this effect. You simply see the information coming from the far distance in a different light, regarding the matter of when it happens. Arguably, this can be taken to mean that there is no reversal of time, as the parts of the universe that reverse in time are those parts that have not been seen yet. However, even this way out still has a flavour that is a long way apart from the Newtonian absolute and universal time that flows without regard to anything else. At this point you might be wondering, yes, but what is really happening? Well, the core of this is that there is no method to come up with any consistent, singular, objective way to answer that question. What can be determined is the relation between the different nets of clocks and rulers laid out in space and time. But none of those networks has any justification to be called the space and the time. There is, however, one rule that might assuage. Events that are close enough to you are certain to keep their order, at least. Some events are close enough in an objective sense that different inertial frames agree on their order, if not their time or rate. These events are said to be within each other's light cone. They are close enough that light can travel between them, but events further apart, not within each other's light cone, can change order, but never when it is possible to actually observe them doing it, only in retrospect. It is in this sense that some people, not myself but nevertheless, say that the speed of light is better described as being the speed of causality. The barn door paradox. Consider a car that is too long to fit in a barn. Run the car through that barn at high speed. It is shorter and so may fit in the barn. But then to the car the barn is shorter and the problem is even worse. When the car is inside the barn, close the doors. Does the car fit or not? This is the most direct introduction to the rookie mistakes. Honestly, I think calling them paradoxes gives them too much legitimacy regarding computation with relativity. They're not paradoxes but misunderstandings. The barn door paradox uses the naive principle that a car moving near the speed of light with respect to the ground will be shorter in the ground frame. I also hesitate to say appears or will be measured, because often this is interpreted as meaning that it is some kind of optical or other illusion. But the idea that this is an illusion is a delusion. Despite what Einstein said in Special and General Relativity, the popular book, the Fitzgerald contraction is not an extra assumption to fix up the theory of electromagnetics. It is a rigorous implication of Maxwell's equations. At least it is if we assume that matter is electrical or analogous to electricity, and it does turn out that quantum field theories are, in the sense meant by Poincaré, analogous to electromagnetics. Solve for the electric field around a stationary point negative charge, for example, an electron. It has spherical potential shells. Solve for a moving charge. This means an electron that has a kinematic or coordinate velocity in the coordinate system in which it is assumed that Maxwell's mechanics works. The resulting potential is ellipsoidal, contracted in the direction of motion. And that means that the natural length of bonds in that direction will be reduced. Any piece of material, such as a block of concrete, will contract in the direction of motion without stress. The reason it is without stress is not magic, but precisely the same reason that it has no stress sitting on the desk. Each bond is at its natural minimal energy length. This seems to imply that there is an absolute velocity, in the sense that the ellipsoidal nature of the field betrays the speed of the electron. And this was an initial interpretation of the result. However, a detailed examination of the signalling between atoms in the material shows that the time coordinate is skewed as well. It just took a while for people to trust what the mathematics was saying, and it can be shown that a travelling scientist will not be contracted in their own frame, but will see the ground as contracted. This is just to mention the idea. It is out of scope of this essay to demonstrate this point and discuss the impact of Voigt versus Lorentz gauge choice. The upshot is that in the ground frame, the contraction of the high-speed car is real. So, if there is a barn that the car would not have fitted in when stationary, it might yet fit when travelling fast enough, though it will only fit briefly because it is travelling through the barn at high speed. On the other hand, the contraction of the ground in the frame of the car is just as real. So from the point of view of the car, the barn is even shorter, and there is no way that the car will fit in the barn now. Well, in the ground frame, the doors are shut briefly at the same time while the car is inside. This is a description from the ground frame. The problem is to work out what this looks like from the car frame. It seems naively that if the two doors are shut at the same time, there will be a rending crash. The simple explanation comes from the relativity of simultaneity. This effect is easy to remember intuitively with the following natural phrasing. When the car travels across the ground at high speed, it sees ahead of it the future of the ground, and behind is the past. This point should be clarified. The car driver looks out the window at a clock on the ground, thus finding out the time on the ground where the car is. At different locations, the time on the ground will be different. Check out the Lorentz transformation and see that the time in the ground frame, as measured in the car frame, increases ahead of the car and decreases behind. This statement does not imply any psychic abilities. Any attempt to communicate the information about events in the future to the ground frame will encounter sufficient delay due to the finite speed of light that the information will arrive too late. Getting back into the barn, the car sees the future ahead and so sees the exit door close first and the entry door close after. In fact, it will see the exit door open again before it sees the entry door close. So from the driver's point of view, the exit door was closed and then opened before the rear of the car was inside the barn. Then, when the front of the car was out of the barn, the entry door was opened and then closed. This gives the sequence of events as experienced by the driver and shows that the idea that in the ground frame the car is shorter and in the car frame the barn is shorter is quite compatible, even when someone tries to shut the car in the barn. Whether or not it was so shut is a matter of point of view, because it involves requiring events that are too far apart to communicate to occur in the right sequence. The sequence of distance events in relativity is relative. Bell's spaceship paradox. This is another case of, do you really believe in the Fitzgerald contraction? Consider two cars joined by a chain. The chain has just enough tension in it to keep it straight. To avoid complications, put the cars in space and call them spacecraft. There is just a small amount of tension to keep the chain straight. The spacecraft are stationary in an inertial frame, which is called the ground frame. Now, suppose that these two spacecraft, as experienced in the ground frame, start moving faster in exactly the same way. This cannot be constant acceleration as measured in the ground frame, as that would require the spacecraft to eventually exceed the speed of light, but it is convenient to use the idea that their relativistic momentum increases steadily with time, which is a sort of booby-prize version of constant acceleration. It does correspond to a constant force, though. The core question is, does the chain snap? As experienced by the ground frame, the length of the chain is not changing. This sounds like a perfectly acceptable state of affairs. Surely the chain does not snap. But taking into account length contraction in reverse, the rest length of the chain is now significantly longer than its original rest length. So that means it is stretched and should break, which is correct. It snaps. Consider a spaceship increasing velocity and assuming that at each point in time it has a length associated with that velocity as a uniform velocity. Then, as it accelerates, it must contract. But if it contracts, then the prow of the ship is getting closer to the stern, so the stern is catching up with the prow, and that means the stern is actually travelling faster than the prow, at least while the ship is accelerating. This is the condition for the ship to remain the same length in the ship frame. So if the ship does not contract, if the stern does not go faster than the prow, this means the ship is getting longer and is under terrible stress and will break apart. And so too does this happen to the chain. My concrete block paradox. Consider a concrete block. A concrete block does not compress well. If a concrete block is placed between two metal plates with hydraulic rams, not the ones with the big horn swimming in the river, pushing them with sufficient force, then the concrete block at first barely changes, and then it fractures catastrophically. Consider a concrete block accelerated up to near light speed with respect to an inertial ground frame, so that the Fitzgerald contraction is 2 times. The block will, in the ground frame, be half the length it was, but it does not fracture. In a co-moving inertial frame, it is still the same length. Someone sitting on the block will see no reason for the block to fracture. Indeed, they might argue the concrete block sitting on the ground should fracture about now. Co-moving inertial frame? What about the frame of the block? There is no such thing as the frame of the concrete block in exactly those terms. There is an inertial frame co-moving with the block, but the concrete block is not in that frame any more than it is in the ground frame. The rest length of the block is not the true length of the block. It is distinguished only as the maximum length that any frame would measure it as. But every frame has an equal right to claim that the length that it measures is entirely true, correct, and valid. Every frame will see the same events. What can vary is when, where, and why. We trust the result in the co-moving inertial frame. This corresponds to our everyday experience that the concrete block does not suddenly fracture for no apparent reason, except perhaps if the contract builder was very, very dodgy. So the block frame, we assert, will not see the concrete block fracture. But since every frame is as valid as any other, then the concrete block is, when working in the ground frame, really, truly, absolutely half the size it should be. It is at a size that should cause it to explode. Which brings up a cooler version. What about a block of uranium? Now, if you compress that to Hart's size, it really should explode. Entirely within the ground frame, and accepting that the block really is half its usual length, we have the serious question of why it does not break into talcum powder. The answer is simpler than it sounds and does not actually involve relativity. It is in fact the motivation for the developing of the theory of relativity. No, not Einstein's version, not exactly, but Poincaré's version, the one that is connected to 100 years of prior physics and experimental results. If I want to analyse a shuffleboard game played on the deck of a ship and can assume the ship is travelling at a constant velocity, then instead of using the ground coordinates of the sliding pieces, which could get complicated, I can use the coordinates with respect to the deck and simply use Newton's laws. The exact same question was posed in the context of the behaviour of electrical currents in a moving fluid during the 1800s. According to the prevailing thought, to see how capacitors and inductors work on the deck of a ship, one simply used the ship deck coordinates and Maxwell's equations. But when this was examined in detail, it was found to be false. The result of analysing things this way conflicted with the result of analysing it from the ground frame. Maxwell's equations appeared not to be invariant with velocity. This was not a conjecture, it was rigorously proven that if Maxwell was right, then this shift in frame did not work. Fitzgerald, among others, worked on understanding this. If you start from Maxwell's equations in a ground frame, how should you modify the equations in a moving frame to work on the deck of a ship? A simple practical problem. Clearly Galileo's velocity transformation did not work. This, by the by, suggested that there was an absolute velocity in the universe, but this was a minor side issue at the time. The problem was the practical one of how to use ship deck coordinates instead of ground coordinates. The particular practical case was the detailed behaviour of an electrical fluid that was flowing. What Fitzgerald worked on, though, was the effect of speed. By using Maxwell's laws and the assumption that the atoms were held together somehow by electricity or electrical-like fields, he solved the equations and found that the correct field around a charged particle at speed is not spherical. You can do this yourself if you want. The core point is that while the field around a point charge is spherical, the field around a moving charge is not spherical, it's ellipsoidal. Why does a block of concrete not change size or shape when put under pressure? Because the atoms, billions of them, all lined up, resist changing shape. Why? Because due to the quantum electrical forces, they have a natural shape, a sphere. Or perhaps not exactly, but they have some definite shape. What Fitzgerald showed is that the natural shape of an atom at speed is a contracted version of the shape when stationary, contracted along the axis of the direction of motion. So the natural shape of a block of concrete when stationary might be a perfect cube, but the natural shape of the same block at speed will be a flattened parallelepiped. And this is why the concrete block does not fracture at speed, even though it is half its stationary length. And all this just comes from plain old garden variety classical electromagnetics. It was the question of the interpretation of this already established result that led first Poincaré and then Einstein to suggest the ideas that made up special relativity. The generic resolution. In my experience, paradoxes suggested by various people in the context of special relativity are usually resolved by a few basic points. The contraction is real and not an illusion, time dilation is real and is symmetric, simultaneity is relative. This last one being the point that a high-speed craft travelling over the countryside will see a collection of clocks that are synchronised in the ground frame to be not synchronised. This means that watching a flying block of concrete, one sees the front end at a different time to the back end, causing the block to be shorter. Despite immediate instinct, measuring the length of a flying block of concrete fundamentally requires synchronised clocks. Please subscribe to this channel. This is time for the hat. I am, after all, a street performer and need to make enough for a loaf of bread. If you like this and want to hear more, then subscribe and I will have a better chance. If you hated it, why not subscribe and see how deep the poison goes? Here is the hat. Please like, subscribe and share this video with your friends. This will give me the opportunity to produce more of these, and if you feel that anything was unclear or incorrect, or if you want to know my opinion on some detail or other, please leave a comment to that effect. Thank you.